So my name's Andrew. I'm usually a tech lead and developer, and I'm based in Melbourne most of the time. Today I'm going to be talking about migrating from a monolith to a modern data architecture. I'm sure many of you have seen this kind of thing before, but it can be as complex and intricate as open heart surgery. In order for you to be able to tackle some of these procedures yourself, I'm going to hopefully give you some tools that are going to help. So we're going to cover a few things in this talk. First up, we're going to look at some common symptoms that you might see in your own patient. We'll go over why monoliths might not be serving us as well as they used to, and the sorts of pain that they might be causing us now. And then next, we'll offer a diagnosis. We'll try and unpack what a modern data architecture might look like. And then finally, we'll look at some of the common treatments you can use for your patient. I'm going to introduce you to the data patterns catalog, which is a thing I've been working on, and we'll walk through some of the ideas in there that'll help you with your migration approach. So first up, why would we want to move away from monoliths anyway? Enterprise monoliths have been around for a long time. If we think about mainframes that retailers or financial organizations have been running for 30 or 40 years, they've enabled these businesses to operate in a relatively smoothly and grow for that whole time, which is a pretty amazing achievement. It's really, really hard to get that kind of long-term stability. And we often have a similar story in the startup world. They usually don't have huge mainframe systems, but they usually do start out with a monolith. This allows them to grow while focusing on their customers without having to develop skills across a whole lot of different capability areas. If your monolith persists for the first few years or so, that's still a really valuable thing. We also often forget about our data monoliths. The enterprise data warehouse pattern was popular for quite a while. It still is. I'm working with organizations today who are still using it. They've usually worked because they're supposed to contain all the data from disparate sources across your entire organization. They store your current and your historical data in a single place that makes it supposedly easy to create analytical reports for workers from across that organization. Enterprise data warehouses were supposed to allow full access to data without compromising security or data integrity. So monoliths can often be useful, but what are some of the symptoms that we need to watch out for? We can usually identify the point at which a monolith becomes a problem. It's when they've become too large to manage effectively. They get to a point where they're prohibitively expensive to enhance, fix, or maintain. Change to monoliths can come with unintended consequences because they're so very entangled. You fix something over here, and then over here something else breaks. Teams working on monoliths are often organized horizontally. For example, you might have your middleware team and your DBA team. And this means that teams will often have to wait for other teams to complete a piece of work. Monoliths also tie you to a tech stack, making it difficult to grow with new technologies as they evolve and mature. Due to the size and complexity of the code in these monoliths, it's usually time-consuming and therefore expensive to onboard new developers because there's so much to learn. You can forget about bringing in contractors or consultants because the ramp-up time is it's too much. So as monoliths grow, they often bring with them a huge database, which it makes changing your data architecture particularly difficult. Domain entities within these databases get tangled with each other, which makes extracting a single entity from the database nightmarishly difficult. The data warehouse pattern requires organizations to have a single enterprise-wide data model, and these are usually hideously slow to come up with in the first place, and often very slow to change. In these systems, your storage format is really coupled to the consumption format, which means changes need to be thoroughly vetted so they minimize the chance of breaking everything downstream. So here's the thing. Speed to market is critical for a modern business. In a modern digital organization, data should be informing all your business decisions, right? So if you can't get your data quickly in the right form, then we've got a problem. So what does a healthy patient look like? Let's say we've decided that we're going to start to do some surgery on our monolith. We want the system to give us speed to new insights. We want to go faster. We want real-time insights, decisions and reactions. We want rapid feature delivery so we can build features around those insights. And we want to support team scale because we want to grow our organization so we can build more stuff more quickly. So our systems, both our traditional software systems and our data systems need to be able to change incrementally. We want to be able to de-risk changes by enabling us to make small bets and perform experiments as opposed to monolithic investment in large-scale projects. We want to be able to fund pieces of work based on continuing adjustment and refinement towards success rather than conforming to a plan laid out at the start of a several-year journey. Our systems need to be able to support these incremental changes and experiments, and that means small, well-encapsulated, loosely coupled applications. Our systems need to be able to scale, both for load and throughput, as well as for our teams. If we're running our data on business, then we'll need to be collecting increasing amounts of it and making it easily available to a growing number of users. We're also going to scale our number of teams working on those systems that channel data. A modern digital business must be technology driven, so we need to grow our teams. If this growing number of teams can't work autonomously and not step on another team's toes, we're going to be in trouble. Our systems also need to be reliable. Systems are becoming more and more distributed, so our systems need to go beyond simply coping with the myriad of random issues they can experience. Modern systems need to thrive in this unreliable, massively distributed environment. And we also need to have data integrity. We need to know that our data is correct. We don't want to think about the impact to our business if we're letting our humans and machines make decisions on the wrong data. We need to be able to trace our data back to its source, track it through enrichment or derivation, and know that we've still got solid data. Ultimately, we want our applications and our overall systems to be better than the ones we have today. More robust, correct, and evolvable. So, onto the treatment. What does one of these things actually look like? I'm going to show you an emerging collection of principles and patterns. We're starting to see these ideas take hold across more and more businesses because we can use them to drive us towards the evolvable, scalable, reliable, and correct systems that we need. So here are the architectural patterns. Asynchronous events are great for decoupling and modularizing your architecture. This is closely related to the application architecture pattern event sourcing, where we communicate changes in state as immutable events. An event is a small, self-contained, immutable object containing details of something that happened at some point in the past. An event should contain a timestamp to indicate when it happened, and we can store events in an event store that is append-only, and updates and deletes are strongly discouraged. Events are designed to reflect things that happen at the domain or business level, rather than as low-level state changes. For example, we might store the event, attendee cancelled their tickets for Voxxed Melbourne. This event clearly stores the intent of a single action that relates very strongly to our domain, whereas the side effect, one entry deleted from the allocated tickets table and one cancellation reason was added to the feedback table, embeds a lot of assumptions about the way that data is going to be used. If we want to add a new feature to, say, allow that we can offer tickets to the next person on the waiting list, the event sourcing approach allows us that new side effect to be easily chained off the original event, rather than having to encode all that logic that is coupled to the original implementation. Immutable log-based message streams are great for simplifying your data pipelines. It provides everything that needs data a single place to get that data from. Apache Kafka is the poster child of this space, but there are plenty of other options for a myriad of use cases, such as AWS Kinesis. Immutable log-based systems also give us loose coupling, which I'll dig into a bit more in a bit, because I think it's a pretty important part of this whole thing. And in the microservices architecture, which models applications as suites of small services that are independently deployable and scalable, blah, blah, blah. The big thing about microservices is they enable teams to build in the most appropriate languages and frameworks and to work autonomously and independently. This style of architecture is great for growing an engineering organization. If we think about the massive growth that Uber has had, they went from a handful of services to 2,000 or something, within a couple of years. That sort of explosive growth, whether it's good or not, we can do it if we need to. So none of these are new ideas. The relatively new part is sort of smushing them all together. We're seeing a convergence of microservices and data. I've heard it described as we take our application architectures, which used to sit over here, and our data stuff that used to sit over here, and we've kind of just smushed them together. So we've got our events, our log-based streaming, and our microservices. So we've just got We've now got small services that consume and produce a lot of data. Seems simple, right? So when we start to do this, we get to take advantage of this idea of unbundling the database, or turning the database inside out, which is an idea originally sort of proposed by Martin Kleppmann, who wrote this great book called Designing Data-Intensive Applications, and Jay Kreps, one of the original designers of Kafka. So their original thesis was that we can provide services with a kind of database that they can share, avoiding the strong coupling and shared mutable state that we get if a lot of applications share a single database. But the loose coupling comes from the fact that we have a simple interface that this unbundled database provides. All we can do is seek and scan. That's it. Any coupling that we have comes from the data itself. So we can take that loose coupling to an extra advantage. Unbundling the database also allows the different components of our systems to be developed, maintained, and improved independently from each other, which enables them to be worked on by different teams. And events can provide a stable, well-defined interface to other types of systems. Asynchronous events also make the whole system more robust to outages or performance degradation of individual components. If any one particular consumer runs slow or even fails, the event log can buffer messages, allowing producers and other consumers to continue running unaffected. The dodgy consumer can then catch up when it becomes healthy and won't miss any messages. If we add a query layer on top of that log, services can still retain control of what queries are run, the hardware they run it on, and what transformations are applied to create the views, and most importantly, when and how these things are changed. It is this level of control, when compared to traditional centralized databases, that keeps services nimble and agile. When a service needs to release, all the highly coupled pieces are already inside its deployable unit, and then only the data itself is shared. So that's where we kind of want to get to. I'm now going to give you some of the tools that you can use to move towards this sort of architecture. The Data Patterns Catalog is a collection of maneuvers, concepts, and guides for building your own data platform roadmap. This is something I've been working on for a while. It's still in the works, but even now there are some useful things in here. The key idea here is that moving to an event-driven architecture gives you a few more levers you can pull when you're planning your roadmap. Some of you will have come across some of these patterns before, but they might be a little different when we're working in this style architecture. Hopefully you'll be able to use some of these to come up with your own plan for treating your patient without stopping the blood flow. So the first one is the strangler pattern. Most of you will have seen this at some point, particularly if you've worked in any OO languages or read any of Martin Fowler's refactoring work. We can take this idea and sort of apply it at a macro level. So if we start out, we've got our monolith here. Very boring monolith. We want to take the blue one, the slightly lighter blue, and we want to extract that one from our monolith. So the first thing we're going to do is we're going to shove the green thing in there, which we call it's essentially an event gateway. It's a load balancer, proxy, nothing really new there. And it's just, all it's going to do is pass data through from either direction back to where it needs to go. Once we've got all the data flowing through that, we can essentially duplex that data, and we can fork it, start copying it to a new version of the blue service that we've pulled out. So as soon as we've got something deployed there, it can start receiving data. And we can start building up the functionality that the new copy of the blue one that exists outside the monolith as it evolves. Once we've got data flowing into that, it can start to produce events which describe the state changes that it needs to see. And then once we've got events flowing, what we can do is we can hook up the consumers on the outside to start reading from the events rather than from the service directly. And then the original, the purple thing that was sending data into the blue, into the monolith can just redirect to speak directly to the new service on the outside. And then we can remove the blue one. So it's looked simple. I've never seen it actually be this simple, but it's very similar to what we do inside like if we were extracting a class or moving stuff around in a traditional OO type system. So that sort of works really well when we don't want to change. Like we don't have much ability to change what happens in the monolith itself. So if you think about a mainframe system, for example, like often those things are really expensive to change, or they might be like just way too coupled to anything else. So we want our changes to happen outside. In a monolith that's easier to change, another option that we have is to identify event seams, which are places in the monolith that where it's fairly obvious that change state relating to particular entities. They'll be often really easy to spot in a monolith that has a very clear domain model, and it's kind of evolved over the years with that strong domain model. If the model needs a bit more work, we can just sort of refactor it to get to that point where we can really see that event seam start. Once we've got that, we can see where the state change is happening. We can start to emit events directly onto the event stream, and then we can start consuming those events somewhere else. What happens here is the event itself has become our interface, and that other components, other consumers, other producers can depend on that interface, and as long as that interface is fulfilled, we can move the code that produces that event anywhere we like. So if it was originally in the monolith, we can essentially just pick it up and move it out. We've also got batch to event adapters. What we're trying to do here is establish the source of truth in an event stream for a particular entity, but we might have split responsibility for that entity in a service that only deals in batches, particularly file-based batches. And it can't be changed very easily, particularly if you think about a COTS product. So what we're going to do is first proxy the batch using a migration gateway so that downstream services are not affected, and then we can create a batch to event adapter that receives the batch dump, translates it into individual file events, and pushes them to the event stream. So here's we've got our batch producer and our batch consumer and our happy event stream down there. So in this case, we don't want to change the batch producer. So we stick one of these magical gateways in the middle. All it's going to do is start forking traffic off to the batch to event adapter. The batch to event adapter is going to take those files, or take that data, start converting it to events, and push those onto the stream. Now we've got events that the batch consumer can start to consume those, and then eventually we can take away that migration adapter. And we've just broken the coupling between the batch producer and the batch consumer. And then if we need to change, we can do whatever work we want to do with the batch consumer because we're depending on that interface now. We can also go the other way. We can go from events to file batches. So again, we've got at least some source of truth in an event stream for a particular entity. But in this case, we've got the consumer isn't as easy to change. So here's our starting state. We've got a system A, it's producing events. We've got B in the middle that we want to get rid of, and we've got C out on the side. So in order to, we want to get rid of B. So we've got events coming from A. So we can start to build up a read model of C from those events. Once we've got that read model, C can pull whatever data it needs from that read model, and now we've broken the coupling between B and C. And then we can, and then we're good to start to start to tinker with B, to either move it out to somewhere else, or A can eat it, or whatever we want to do with it then. Cool. So there's a few more patterns in here, but one of my favourite ones is sort of the things you need for self-service data governance. In order to make any of this work, there's a whole lot of governance that we need to enable, and it's usually a good idea for us to do this in a self-service manner. As we know, if a team who wishes to start producing events has to wait for approvals and lots of modelling, and all the blah blah that can happen, it's going to slow down and we're going to lose any market advantage that we might have worked really hard to get. Two of the first capabilities that you might want to implement to enable self-service data governance are a data catalogue and a schema registry, or some combination thereof. First off, we're going to use some sort of schema to describe the structure of our events down to the fields and data types. Whether some piece of data conforms to a schema can also be checked at different points in the data's lifecycle. We can start to make assertions about the compatibility of a particular change to a schema for downstream consumers, which is kind of it'll act as a contract between our producers and our consumers. And there's plenty of options for the format of these that we can choose. There's Avro, Parquet, Protobuf, Thrift, like a whole ton of things that are really useful. I'm quite fond of Avro, mostly because it separates the ideas of a writer schema and a reader schema. So for any given schema, they don't have to be exactly the same. You don't need, we're not directly coupled to a particular version of a schema between a producer and a consumer. They only need to be compatible. This opens up a world of joy for us when we want to evolve the structure of a particular event type. There's a certain check that we can, a whole pile of checks that we can do on our schemas that infer that we've, the change that we've made will be compatible and safe for our consumers. We also need a data catalogue. This is a key element of a data platform, enabling discovery and maintenance of data sets. Key functions of the data catalogue can include exposing metadata, which might include freshness, access metrics, provenance, allow creating and updating metadata, access control, sampling or raw access to data, searching metadata, governance of the required metadata fields. The schema registry will provide much more detailed information about the specific structure of data within the event stream. So key functions of the schema registry are to provide the data shape for events in the system, and then for use by operational systems, for instance, for data serialization and deserialization. The event stream itself can enforce conformance to the schema registry, preventing ingestion of events with schemas that are not in the schema registry or that have inadequate metadata, which helps us when defining the integration contract between services. And if you set up some kind of mapping of event types to topics or streams, for example, then the schema registry can provide you some kind of discovery mechanism. And if you've got a good one, you can wrap it in some search and stuff, and it makes it really nice. So another key bit of this puzzle that we've seen a lot, a growing interest in recently, is the process of observing all data changes written to a database and extracting them in a form which can be replayed to other systems. Change data capture is particularly interesting to us if the changes are streamed at the same time as they are written to the original database. For example, we could capture the changes in a database and continually apply them to a search index. If the log of changes comes through in the same order as the original writes that we get from our log-based event stream, we would expect the data in the search index to match the data in the original database. All of these secondary indexes and all other derived data systems are just consumers of the event stream. The way I've recently used this at a client is to extract data from a source database and transform it using stream processing tools into a valuable domain event. We've got some pretty robust tools for this these days. We've got Debezium and things like Maxwell for MySQL. There's more Debezium for Postgres. We've got Golden Gate for Oracle, and there's plenty of other platforms. Kafka Connect also offers an API in which you can plug a streaming data provider like a CDC adapter. So there are quite a few other open source CDC tools that make it really easy to get started producing change events from a database onto an event stream. So if a traditional database transaction mutates several objects in your database, it is often difficult to tell after the fact what the transaction means. Even if you capture the transaction logs, the insertions, the updates, and the deletions in various tables, it doesn't necessarily give you a clear picture of why those changes were made. The invocation of the application logic that constructed those events, those changes, is transient, and you can't reproduce it easily. Event-based systems, on the other hand, can provide much better auditability. In the event sourcing world, any change to the system is modeled as a single immutable event, and any resulting state updates are derived from that event. This derivation should be deterministic and repeatable, so the running of the same log of events through the same version of the derivation code should yield the same state. This makes the provenance of data much, much clearer. Data integrity becomes much more feasible to check. For the event log, we can use hashes to check for corruption. And for any derived state, we can repeat the processing to see if the resulting state is the same, or run the same processing in parallel to try and identify where things are going wrong. This sort of determinism makes it much easier to debug and trace the execution of the system as a whole in order to understand why something happened in the case of where something failed. So we've got some cool enrichment patterns in an event streaming world. We can start to think about stream processing a bit like Unix pipes. We can pass streams in and we get streams out. We're defining single units of responsibility, which allows us to derive or enrich by composition, which becomes a really powerful thing. We can do, if we use KSQL, which sits on top of, on Kafka, we can do this much code to consume one stream, do some stuff to it, join it with some other stuff and spit it out the other side. It gets, it makes these pretty nice, and deploying this on another hand is can be tricky, but if we think about this as a single unit of transformation, then the power we get from deploying a few of these around the place and being able to compose these small units to create data pipelines is kind of powerful. So one of the things we need to think about with this, as the microservices leaning of this architecture suggests, is there's no single tool to run them all. We're not getting rid of databases. We're not unbundling the data doesn't get rid of the need for that. We still want. I still wouldn't trust an event stream as my system of record in most cases. So we still want very robust, reliable systems around our event stream to provide that, like the durability and the trustworthy storage that we need. However, this does give us an interface into that data. So we've still got those. We want data stores to pump data into for secondary indexes, for a whole pile of other tooling around it. So we still need other things. This just opens up ways to move data around. And one of the big things to take away from this is something that you probably all know from having worked with big data systems, or big systems in general, that we can't guarantee that every bit of hardware that we have, nor that every bit of software is fault-free. We need to periodically run end-to-end validation of our data for integrity, reliability, and auditability. If we don't check, we're going to find out about corruption way too late, and it's potentially caused significant downstream damage. If that happens, it's going to be very expensive and very difficult to track down the problem. End-to-end data integrity checks will help us exercise the breadth of our technology that supports our data. The more systems that we can include in these checks, the fewer opportunities there are for corruption to go unnoticed. If we can check an entire derived data pipeline is correct from end to end, then in theory, the disks, networks, services, and algorithms along the path will also be included in those checks. Ideally, these checks will be run in a continuous fashion so that we can increase our confidence in the correctness of our systems, which helps us to move faster. So we can do other stuff. I've got a whole pile of other patterns, including reprocessability, a whole more and more stuff on enrichment. But I think we might finish there. So I'll leave you with that. If this was interesting, there's a written version coming soon. It's slowly coming together, but we'll have a documented place to share and discuss these sort of patterns, which I'm pretty excited about getting finished finally. And if you want to talk more about data architecture and engineering, I host the Data Engineering Melbourne meetup. Our next edition is going to be on Thursday, the 30th of May at 6 p.m. in the ThoughtWorks office in the city. Look us up on Meetup if you're interested. But otherwise, thank you.